Hello and good morning, everyone. One reminder for you is I sent out I posted on Piazza last night and forced an email to send to everyone. There's a Google form that we want you to fill out, which is telling us which time you would like to take the final or the midterm exam. So there's basically lecture time or 12 hours off of lecture time. So it'll be starting at 10:20 Ann Arbor time, either AM or PM. So make sure you fill that out so that we can assign people to time slots. It's not as convenient for us to give it at two different times, but it is going to be a huge benefit to people who are in different time zones. The other thing I wanted to point out is that when you pick those time slots and the day you take the exam, it is up to you to follow the honor code. If you decide, hey, I think I'll tell a friend of mine who's taking it later in the day what that written question was that was hard, and I'll just tell one or two people, it won't be a big idea. Well, if you tell two people and that person tells two people, in about 6 handshakes or so, everybody taking the later exam is going to know the question. And then they're going to effectively get higher scores than you are, and then they're going to get better grades than you are. So you can hurt yourself if you want to, but I would suggest against it. So today we're going to be talking about elementary sorts. And so the idea here is that we want to put some sort of data into a sequence by some key. And by key, I mean we might have something like, say, a collection of student data, and I want to put them in order by name. So we're going to use, by default, we're going to assume that the data type that we're working with has operator less than, and that we will produce an ascending sort because we're receiving an operator less than. If we want to produce a different ordering, we can use a different comparison. Today we're going to look at a couple of elementary sorts: bubble sort, selection sort, insertion sort, and counting sort. And we're also going to be talking about, or have already talked about, we already talked about the high performance sort heap sort. In future lectures, and the slides are already posted for those, we're going to be talking about quick sort and merge sort. And there's another sort I want to mention called radix sort that we're not going to talk about, which is very creative. There are tons of sorts. There's another couple sorts that we're going to mention after we get quick sort done. We're going to talk about intro sort and how that works, and I'll mention another sort. And there's shell sort, which is almost impossible to analyze the computational complexity. There's smooth sort. There's all kinds of sorting algorithms out there. So we want to talk about some that will give us a basic idea of how the elementary sorts work and how some of the more high performance sorts work. Now, these elementary sorts, just because they're elementary sorts doesn't mean they are useless. They give us a couple of nice things. So one is that we can look at how we have different approaches to solving the same problem. We can look at how we have, when we have multiple solutions, how can we compare their complexity and their advantages and disadvantages in certain situations. We can look at optimizing code and how to make a particular set of code faster. And also sometimes we'll look at how to make these more memory efficient. None of them today, although in the future lecture we're going to look at memory efficiency and how to improve that. The elementary sorts are also sometimes good enough when we have small enough amount of data. It doesn't really matter which sort we use if there's 20 items. It's also, sometimes these are very good in particular situations if I know something about the data. We'll also look at how these can be combined with more sophisticated sorts. And after we do, or as part of doing quick sort, we'll talk about intro sort, which combines several different sorts into one overall algorithm. Now, today we're going to be talking about arrays, or we could use it on any data type that has an operator square brackets that's O of 1. So everything we're talking about today we can apply to an array. We could also apply to a linked list. It would take a little bit of effort to write, but the elementary sorts tend to be able to not only be, and when I say we can do it with linked lists, we can implement any sort with a linked list, but our real goal is not just to implement it, but also to have no loss of complexity. I don't want to go from, say, n squared to n cubed. So when I say all the ones today can be implemented with linked lists, not only can they be implemented with linked lists, if we're careful, we can do it without increasing the computational complexity class. Now, if really what you want to talk about is bands and other things, I'd be happy for you to go somewhere else and talk about bands. If you're going to be attending lecture and you're paying for this, I would think you would want to pay attention to what you're paying for, which is computer science. Now, some tasks are better suited for arrays. Some of them can be adapted to linked lists, and all of the elementary sorts can be adapted to linked lists without losing complexity. Now, when we look at the STL algorithms all work on iterators. And because they work on iterators, they can work on any container whose iterators support the operations that they're doing with those iterators. So, for instance, if a particular algorithm says it accepts random iterators, then it could operate on an array, it could operate on a vector, it could operate on a deck. All of those have random iterators. If it uses something specific to random iterators, then it wouldn't work on a linked list iterator. Now today we're going to be using indices and arrays. And one thing you could try later on is rewriting these algorithms using iterators. It would be fairly easy to rewrite them assuming in a random iterator, a random access iterator, because random access iterators allow the pointer notation, which is things like dereference of iterator plus I. It's where I is an integer or an index, or we just say it's a number. So we can do iterator plus number, which is also supported by pointer plus number. So that's one thing you could try later on, is rewriting these using random iterators would be easier than writing it using, say, forward or bidirectional iterators. We are, however, in this lecture, we're going to assume that when we give, when we give you two indices, left and right, that we have the same sense as iterators would have of the left index is inclusive, the right index is exclusive. And so that would make your job easier translating these to iterators, since we're being consistent this way. Now, when we look at sorting, for the most part, things that you've considered sorting up until now, they all fit into memory. I can see all the elements, they're all in this array, or they're all in this vector. And the entire sequence that I want to sort fits in memory, and we assume also when we're doing this, we've got O of 1 time random access to get to an element. In an indirect sort, we might say, hey, and Professor Darden looked at like index sorting in a previous lecture, how to use the STL to produce an index sort. We would reorder the indices, or we could also do it with pointers. And if we could do it with pointers, we could do it with iterators. But really, iterators iterators and pointers are kind of specific to it being in memory. So that's why we tend to stick to indices here. Or we could say just a general location. Like, for instance, the data could be on disk, but I've got a copy of the keys in memory. So the data is large. Like, let's say I've got medical records. I want to sort medical records by, say, blood glucose level or blood oxygenation level. I don't want to reorder all of those medical records, but I've got a single number that I could say, hey, I've got single numbers that I want to use to sort, and they refer to a particular patient's medical record out on a file somewhere. And I could keep those blood glucose levels in memory along with the index and sort them by their glucose level without actually reordering the data, because copying and moving around those patient files on disk would be really expensive. Another sort beyond that would be, I can't even fit all of the indices into memory at the same time. And we're going to talk about this more when we talk about merge sort, which was designed for sorting things actually on tape drives, which I know really, really out of date. But we'll talk about that more when we get to merge sort. So today we're going to be dealing with internal sorting. When we're doing internal sorting, we're going to have a couple things that we're going to assume that we have. We're going to have an operator less than. We're going to assume that our data has an operator less than supported by its type. If you want to remove that assumption, you would have to pass a functor to the algorithm and the implementation of the function, and then use it like we did last time with our set union. You would pass it the comparator, and you'd use the comparator in an if statement. Like I said, we're assuming we've got operator square brackets and that it's old 1. And if we remove that constraint, then we could work with linked lists. We're going to assume we have a swap function so that we don't have to write the code to swap the contents of two variables every time we want to do it. And we're going to take a look at doing that in just a second, how we would write that. My sort, there's going to be a couple different sorts today, named like bubble sort, selection sort, insertion sort. They're going to be named after their algorithm. And we could, we're not going to show one today, but we could create a main that did something like, hey, I'm going to fill an array with numbers like we did back here. I'm going to fill an array with numbers here. I'm going to call my bubble sort function, and then I could add a little more code after this to output what's in the array after it's done. And then if I do that enough times with large enough arrays with enough different values, I would get an idea that, hey, this probably works all the time if it works in enough tests. And we could also use this driver here. A driver program is one that doesn't really accomplish a task. It doesn't do like a pirate treasure hunt or anything like that. It just shows you that a particular algorithm is doing what it needs to do, and that your implementation of that algorithm is working. And we could also do things like we could modify the algorithm to output things like, hey, let's look at what the internal contents of the array are at each step during the sort. I could add some output statements inside of the code for a particular sort. Now, if we don't say otherwise, and this is not just today, but this is for the rest of the semester, is unless we say otherwise, you can assume we mean an ascending sort. If we want a descending sort or something else, we'll tell you that, or we'll provide you a functor that does it. Or in the case of the projects or the labs, we would tell you what has to be done, and you'll give us the functor that makes it happen. Now, what I want you to do here is take just a minute or two, write a swap function. So we can start out, it's going to be void, because it's not going to have to, whoops, I can't write. I'm thinking ahead, and then I'm writing trying to catch up to my thinking. So swap, and it's going to have two parameters. We can call them A and B. Really, when I write functions, I tend to stick to lowercase for variable names. So write a swap function that's going to swap the contents of two variables. We could make them, say, integers, A and B. And then we'll convert this to a template. So take oh, you did this in 280. Well, it's good practice, right? So, well, then fine. If you did it in 280, let's do it together. So I'm going to erase this a little bit. I'm going to move my swap down a little bit. So I'm going to do void swap. And I'm going to swap integer A, integer B. I can create an integer temp, set it equal to A, set A equal to B, and B is equal to temp. Okay, there's our void swap function. Unfortunately, it does not work. There's a problem with it. And I know you're like 30 seconds behind me, so I'll probably have like 6 people answering this by the time I get around to doing it. So what's the problem with this? Why doesn't this swap work? Because we pass the variables, we pass the parameters by value. So we need to change these. I left a little space here. We need to change these to reference to A, reference to B. Yep. And now it works. So we create a temporary variable, set it equal to A, set A equal to B, set B equal to temp. So that works fine. Now that it works, let's do it. And yes, you're right. We could do it by pointer. The problem with doing it by pointer is then I have to do a address of when I call swap. I've got to do a dereference inside the code, and so that would be a little bit more work. Generally, we want to do it by reference rather than by pointer. Pointer would work, but it puts more overhead on the person using it also. The person using it has to take address of elements. Now, if we want to convert it to a template, we're going to add our template header. And when we say template, we can say either class or we can say type name. They both work. I'm going to say type name because it reads better, but if I was doing this on the exam, I might say class just because it's 5 letters instead of 8. It's faster to type. Either of them is equally correct. So we say type name. We've got to give it a name for the type. When we name a type, I tend to name my type starting with capital letters. And with templates, especially short ones, it's not uncommon to see people do like a single letter for the type name. Okay, now we've got our type name T. What we've got to do now is we've got to modify our code, and everywhere that we see an explicit type like int, we've got to decide should this change to type T or not. Now in this one, all of these are going to have to change to type T. Now as an example of something that wouldn't have to change its type, suppose that I passed you a vector and we wrote the function to use like an index. And so like I passed a vector of integers and I wrote it really sloppily. I wrote int I for my index. Well, that would be a case where if the type T changes for what the vector contains, I wouldn't change my loop variable to that type also. If I had a vector of strings, my index would still be an integer type. It wouldn't change. I wouldn't index a vector of strings by a string. Okay, so there's our swap, and I've got the solution written out with the code and the template version. And here in the template version, because I could type it, I did type TYPE instead of just T. Now, one thing about doing this is we don't want to do this. Well, that's a good point. So if the type doesn't support operator assignment, then this doesn't work. And we will get what we mentioned when we talked about the STL and using the STL, we would get an error. Even though our code looks fine, it would say there's a compiler error in swap because it doesn't support operator less than. The code, the call to swap looks fine, but it would say, hey, there's an error in this line right here that it can't compile because I couldn't find an operator equals that worked. Now, I started to say don't do this. The reason we don't want to do this, a better thing to do here is to include utility and use the STL version of swap. One reason, it's already written. Two, if we do both, or even if we don't include utility, if I include something that includes utility and I do a using namespace standard, this whole function won't ever compile because it collides with this one. And so the other reason not to do this is that the STL version uses the move semantics for efficiency. For example, if I had two vectors and I call the STL version of swap, and I give it vector1, comma, vector2, it will swap those vector contents in O of one time, because the STL version of the swap knows how to get a vector to actually swap its pointers and its sizes. And so basically, this turns into three swaps: a swap of the sizes, a swap of the capacities, and a swap of the pointers to dynamic memory. And that's O of one to swap three integers or pointers. So that's why we want to stick to using the STL. It can do things more efficiently than we can. Also, not just vectors, if you had a class that you wrote that supported move semantics, the STL move will support the move semantics of your type. Now, when we write an algorithm, we want to have a good complexity. So when we're talking about complexity today, we're going to look at the number of comparisons. We might look at the number of swaps. These are things that sorting algorithms do. They do comparisons. They also do swaps. Comparisons is a little bit nicer because lots of algorithms do comparisons. Searching algorithms do comparisons. If I look at swaps, I can't look at like a spectrum of so binary search. If I look at comparisons, binary search is O of log n, linear search is O of n, and then I get to, say, heap sort has O of n log n. Comparisons are sorts today, like bubble sort is O of n squared comparisons. So if we look at comparisons, we have this nice spectrum that includes other things other than sorting, that we can look at how they compare to each other. But today we're also going to look at swaps, because we'll see that some sorting algorithms may have the same number of comparisons as another sorting algorithm, but less swaps, and that might be really important sometimes. And we're going to look at the worst case, the average case. We'll talk about what might constitute an average case, and we're also going to talk about best case, because sometimes best case is important to us. Well, like I said, Kevin, sometimes if I've got a very small n, who cares if it's efficient or not? With 10 items, I don't need to be efficient. I need to get the sort written right now. And so bubble sorting is an easy one to remember. Oh, I do have support now. Okay, so Professor Darden's here for questions. Great. Okay, so besides our comparisons and swaps and counting those, we also might look at memory. How much memory gets used? Can I sort in place? Like, you give me an array, can I sort inside of that array with O of 1 extra memory? And O of 1 extra memory means a constant amount of extra memory. I might have like a couple of variables for indices. I might have a variable like, hey, while I'm doing a swap, there is a temporary variable there for an instant while the swap is happening, but that's a constant number. I've got a couple of index variables, I've got a temporary variable, that's a constant number, is still O of 1. I might be sorting in place, like inside of your array, but I might have to do recursion to get it done for a particular sort. Some sorts use recursion, some don't. And if I'm using recursion, I might want to consider how much stack space is used. Is the recursion depth going to allow me to use the stack without getting a stack overflow? If we do in the indirect or index sorting, which we mentioned previously, we might have an additional n pointers or n indices to do an indirect sort. And some sorts just need an upper limit that says big omega, never any more than or at least, sorry, at least n extra memory. So some sorts need some extra memory, and we'll look at how that happens with quicksort when we talk about the recursion. We'll talk about merge sort and its recursion and its extra memory for doing the merge step. So we'll look at how some sorts require extra memory. Another property of sorts. We got a bunch of properties before we actually get to the first sort. It's coming soon. So another quality of sorting algorithms and a few other algorithms, but we mostly talk about it with respect to sort, is stability. So stability means if there are duplicate keys, the original relative order is preserved. Elementary sorts tend to be stable, but not all of them are. Complex sorts tend to not be stable. Some of them are. And for example, we've got a page here. Now, to fit this in one slide, I had to put the names in double quotes. I tried to do it where it was like curly braces, quote, Sheen, quote, comma, curly, quote, Charlie, quote. I tried to put them all in separate quotes and to put curly braces around each person, but it didn't fit on the slide anymore. So let's pretend that we've got first name and last name as separate variables. So I've taken this data and I've already sorted them by first name, and then I give them to a sort with a different functor and I sort them by last name. Because they were already sorted by first name, Charlie comes before Martin because they were sorted by first name. With a stable sort, it is guaranteed that Charlie will still come before Martin when we sort on a key that has duplicates. So when I sort on a last name key and the last name key has duplicate values Sheen, when I do a stable sort, Charlie is guaranteed to stay before Martin. They maintain their relative order. Charlie was before Martin before this sort. Charlie is before Martin after this sort. With an unstable sort, they might reverse their order or they might maintain their order. It's hard to predict. With an unstable sort, it might go either way on the ordering. But a stable sort is guaranteed to be in that order. Now you might say, well, hey, Professor Paoletti, why don't we just make a more complex functor? I'm already doing this for Project 2 for my zombies. I've got to break ties, right? I could write a more complex functor that breaks ties. And the reason that is not always a valid solution is, what if I don't know what order some user wants to sort on? What if, I'm going to erase my markings here, what if I've got a web page, and inside my web page, it's got a table of data, and it might have 5 or 6 or 7 columns, and each column heading has a little arrow button to say sort by this column. If I use that arrow and sort by say this is last name and this is first name, if I hit the first name sorter and sort by first name, then I hit the last name sorter and sort by last name, I don't want to keep track of which order the user clicked on the sorting buttons. B, I don't want to have to write n, let's call it C. If C is the number of columns, I don't want to have to write C factorial different functors. That's just ridiculous for a large C. Even 6 would be 720 functors I would have to write. If instead I just use a stable sort, the user can click on them in any order and get the order that might make more sense to them. In fact, when I see things like this, I used a website for a game I was playing that would sort solar systems and planets within the solar systems that would have a certain resource, it would put it in a table. And I was like, ooh, let's find the closest star system to me and the closest planets within them. And it wasn't a stable sort. When I sorted by one and then clicked the other button, they randomly reordered. And I was like, oh, yep, see, person who wrote this website didn't know what a stable sort was. They know how to make websites, but they don't know sorting algorithms. If you use something like Google Sheets and you use the filter buttons where you can sort by a column, it does what I would expect. It does a stable sort because that was written by someone that knew what they were doing. Another thing, we're almost at our first sort. We're almost there. Another type of categorization that we can use for sorts is it not adaptive or is it adaptive? With a non-adaptive sort, the sequence of operations is independent of the order of the data. So for instance, if we see that the best case is O of n squared and the worst case is O of n squared, we would say it's not adaptive. But if I see that, say, the best is O of n versus O of n squared, I'd say, ooh, this is a more adaptive sort because the best case is much better, much different than the worst case. So the adaptive sort might do less work depending on the ordering of the data that comes into it. So if we look at worst case versus best case complexity and we see a difference there, we would say it's adaptive. All right, here we go. First sort, bubble sort. Just a second, I need a drink of water. I've been talking too long. Okay, so our first sort here is bubble sort. This is the non-adaptive version. We're going to improve on this. So this is the simplest version of bubble sort. And the basic idea of bubble sort is I always compare adjacent elements, and if they're out of order, I swap the adjacent elements. And my swap, I could reorder the swap there to do a sub j comma a sub j minus 1. Doesn't really matter. And the basic idea of here is we always compare adjacent items. If we don't like their order, we swap them. The details, like if my outer loop, we can think of the outer loop here as the outer loop is doing passes. Passes through the data, meaning it goes through, passes meaning it iterates from one end to the other. So the outer loop is a pass. The inner loop is the code that's going to actually do one pass through the data. So the inner loop is going to go through my array from one end to the other. The outer loop is going to make that multiple passes happen. Now my inner loop for this makes one pass from one end to the other. The exact details don't matter. I could go from left to right, I could go from right to left, increment, decrement, it doesn't matter here, really. They would both be a bubble sort. But we're going to look at it the way we wrote it here is basically the inner loop starts at the right minus 1. Remember, the left index is inclusive, right index is exclusive. So I set j equal to right minus 1. J is an actual index. So j starts at right minus 1. It says keep going as long as j is greater than I. We'll get to that in a second. And we're going to decrement it. If I don't like the order of a sub j and a sub j minus 1, I swap them. Okay, well, let's look at the outer loop. Outer loop says I have to start I equal to left. I is less than right minus 1, so that's how many passes I've got to make, and I gets incremented. I is basically, so initially I is going to start out at left, which is 0. I is telling me basically how many values I know have been bubbled to their correct position. So after one pass, I know the smallest value has bubbled all the way to index 0. So after the first pass, when I becomes 1, I know that at least one value is in the correct place. And that's why we say I keep going as long as j is greater than I. One reason for j greater than I is, hey, I don't want j minus 1 to become negative. That would be terrible. But that would work if I said j greater than 0. I wouldn't go off the left-hand end. The j greater than I makes sure that I don't compare things that have already been bubbled to the correct position. So if I started out with, for example, 4, 3, 2, 1, I make one pass through the data from right to left. I look at 2 and 1. I don't like 2 and 1, so I swap them. I look at 1 and 3. I don't like 1 and 3, so I swap them. I look at 1 and 4. I don't like their ordering, so I swap them. And I'm left with 1, 4, 3, 2. I just wanted to rewrite that a little bit neater. Okay, so I'm left with 1, 4, 3, 2. When I go to my next pass, I starts out at 1, is saying, hey, there's one value that's already valid. You don't have to compare to that one anymore. So we put a little bit of intelligence in here so we never compare to ones that we know are definitely in the right place. So what I've got here is a slightly larger example. So we've got our initial input, and we go through that initial input, and we make comparisons from right to left. So I look at 1 and 3 look good. 1 and 5, I don't like them, so I swap 1 and 5. I look at 1 and 2, I don't like those, so I swap 1 and 2. Compare 1 and 4, don't like those, so I swap 1 with 4. And there's my ordering. After the first pass, I know the smallest item has been bubbled into that position. So now I compare 3 and 5, those get swapped. Compare 3 and 2, look fine. Compare 2 and 4, they get swapped, and I don't compare to 1 anymore. That's where we are after the second pass. The second smallest item has been bubbled to the beginning. Now we make another pass. We compare 5 and 3, they're fine. Compare 3 and 4, they're out of order, so we swap them, and we don't compare anyone to 2 or 1 because they're in the right place. So we've got another pass. Now we make another pass. We compare 5 and 4. They're in the right place, so we don't swap them. Now there were no changes. Why did I make that pass through the data? Because I didn't know that the data was in order. I had to make another pass. What if the data started out as 1, 2, 3, 4, 5? I make a pass through. I look at 4 and 5 are fine. 4 and 3 are fine, 3 and 2 are fine, 2 and 1 are fine. I make no swaps. Now I know the smallest value is here. On my second pass, I compare 5 and 4, they're fine. I compare 4 to 3, I compare 3 to 2, they're fine. Now I know those are in order. I make another pass. In this pass, I'm going to change colors. In this pass, I compare 5 to 4 and 4 to 3. Now I know 3 of them are in order. I make another pass. I compare 5 to 4. Now I know that 4 of them are in order. Now I can stop. Once I've put 4 values in the correct place, I can stop making passes because there's only 5 values. But in this example, I could have stopped a lot sooner. If I had noticed no swaps happened, I could avoid future passes. So it's not adaptive because of that, because when we bubble sort 1, 2, 3, 4, 5, we make lots of passes that involve no swaps. Let's adapt it. Let's look at it so that when we see no swaps have occurred, we stop making more passes through the data. So here's the modifications required to do that. I added the modifications in red here. So I had to add a Boolean variable swapped, and this is saying basically, did I make any swaps within this pass? I'm going to assume there haven't been any. And if I make one, I mark it as true. I did make a swap during this pass. If I make multiple swaps, we just keep setting it to true. When the inner loop finishes, we check. If I never swapped, I break the outer loop. Alternately, I could put a return statement here also, because we can see when the outer loop stops, the whole function is done anyway. So break or return there, either one would work. So if I ever make it through the inner loop without making a swap, we immediately stop the outer loop, and now we get a better performance when data's closer to sorted. So let's look at an analysis. When we look at the non-adaptive version, there's going to be, it says here, approximately n squared over 2. Really, the exact number here is n times n minus 1 over 2. This is equal to n things chosen 2 at a time. Do you need to know that for the exam? No. But you should get used to seeing this, and remember, this is basically how many comparisons we had to do when we never compare anyone to themselves and we don't compare them to the things that have already been sorted. So we don't compare anyone to themselves, we don't compare anyone to things that have already been sorted. So we get about this many comparisons and swaps in the worst and the average cases. In the best case, we still do all of the comparisons, we just don't do any swaps. In the adaptive version, we'll get in the worst and worst and average cases, we'll get about n squared over 2 comparisons and swaps. Still in the adaptive version. In the worst case, it doesn't change. In the average case, we'll talk about what average means in a minute, it's still about the same. However, when we get to the best case, meaning it's already completely sorted, we do about n comparisons. And in our best case, we do 0 swaps. Now I said approximately n swaps. Think of something that's almost sorted. What if I had something like 2, 3, 4, 5, and 1? We would make one pass through the data where we keep moving this, bubbling this one towards the beginning. So I'd make one pass where I bubble that value to the beginning. I would make another pass where I do comparisons, realize everything's good now, and I can stop. So in the actual absolute best case, we would do 0 swaps. But it would be pretty good. It would be almost the best case if we did n swaps and did 2 passes. That would still be n comparisons. It would still be O of n comparisons. I made about n comparisons on the first pass, about n comparisons on the second pass, and then I was able to stop. So when we get to the best case or almost the best case, we'll have about O of n comparisons and O of n, or possibly down to 0 swaps when the data is already sorted. So the adaptive version of bubble sort is really useful when the data is already sorted or it's really close to sorted. What does close to sorted mean? We're going to come back to that topic a little bit later. So when the data is sorted or almost sorted, bubble sort can do really well. The advantage of bubble sort. So someone asked earlier, why bubble sort? Well, one is that bubble sort is simple to implement. It's simple to remember the overall approach of bubble sort. So it's a nice algorithm because it's easy to remember, easy to implement. It'll work with any language easily. It'll work with any data structure. We could rewrite this with linked lists really easily. We might have to use doubly linked lists if we want to go backwards. But we can implement this with lots of different languages and data structures. As long as we remember the algorithm, the code is really easy to do. The other nice thing is that as we make one pass through the data, yes, we bubble the smallest value to the front, but we leave behind us some of the adjacent pairs are sorted because we didn't swap them. Anything that we didn't do any swaps with is already in the right order. The adaptive version also does a really good job if the data is almost sorted. Like I said, we'll talk about what almost sorted means in the future. The disadvantage is, in the worst case, it is O of n squared time. And because of that, it tends to have a lower performance than our other sorts that we're going to look at, like heap sort, quick sort, merge sort, etc. For this one, I would say yes, you want to make this one adaptive. And if we ask you questions about these on the exam, I've got a slide on this later, but worth mentioning now. On the exam, if we say X sorting algorithm like bubble sort, we mean the adaptive version. So we're going to assume from now on that once we've seen the adaptive version, we're going to use it if it produces any savings. Okay, selection sort. Now here's all the code. Let's talk about the basic idea at the bottom before we look at the code. So the basic idea of selection sort is let's go through and find the smallest value and swap it with the first position. Then I'll look through the rest of the array, not including the one that I've already put in the right place. I'm going to look at the rest of the array, find the second smallest element, swap it with the second position, and we're just going to keep doing this. So that's what the code here is doing. So we've got these outer loop, which is going over multiple passes, and I've got an inner loop here with some code before and after the inner loop. This is one pass through the data. We have to assume where the minimum index is, we do the loop, and then we swap to get that value where it should be. So the pass in this case includes not just the for loop, but the code that precedes and follows it is really the one pass. So it says the outer loop we'll come back to. Inner loop says let's assume min here. Min it didn't fit as well, although yeah, I could have fit that in there. Really, min is really the minimum index. Min here is the minimum index. It's where the smallest value occurs. I should have really just said min index there. It would have fit on the slide. So we assume the minimum index is at I, and I is going to start out at 0. So we assume the minimum index starts at I, and then we're going to loop for j equals I plus 1. I'm trying to find someone smaller than the one that I assumed was the smallest. So I don't have to compare like a sub 0 to itself. I start comparing a sub 0 to a sub 1, a sub 2, etc. So that's why we start j out at I plus 1. We don't want to compare things to themselves. So then I say if a sub j is less than a sub min, remember where we found the smaller value is at index j. So we keep looping through all the data until we've looked at everything. We assumed the smallest was at index 0. We look at everyone else. If we find a smaller one, we know what the minimum index is. And then after the inner loop is done, we swap the min index with a sub I. A sub I has now been selected to be the smallest value. Then we go back through the outer loop. I increases. We say, hey, let's start at index 1 now. Let's assume the minimum value occurs at index 1. Let's start at index 2 and find anyone that's smaller. After we find someone that's smaller, we find the small list. We swap it with a sub 1. Now notice here the outer loop says I is less than right minus 1. The less than and the minus 1 are there. Remember, right is not a valid index. Right minus 1 is a valid index. However, we don't need to make n passes through the data. We're going to make n minus 1. And this was true in bubble sort also. I didn't point it out. We're going to make n minus 1 passes through the data because if I select the n minus 1 smallest values and put them where they belong, the biggest value has only one place left to go. It's going to end up in the highest index anyway. So we don't need to make n passes. We only need n minus 1. So here's a new slide with some initial data. So we start out, we say I is equal to 0. We assume the minimum index occurs at index 0, and we run our inner loop. And we say, oh, look, wait, I've got a smaller value at index 1. Ooh, look, index 2, that's not smaller. Index 3 is smaller still. Index 4 is not smaller than that. All right, so now that's our pass through the for loop. Now we swap a sub I with a sub min. We put the 1 here, we put the 4 over there, and that's 1 passed through the data. I becomes 1, min goes back to, gets reset equal to I, and then we make another pass. We say, hey, I assume the minimum value that's not already sorted. Remember, this region is already sorted. We're not going to change that. We're not going to look at it. We look at index 1. We say, I think index 1 might be the smallest value so far. Let's see if we find anything smaller. We don't. We look at 5 compared to 2, 4 compared to 2, 3 compared to 2. We never find a smaller one. So when we get to the swap, we say swap a sub I with a sub min. Basically, 2 swaps with itself. Now, after that, I've got 2 of the values are sorted. I starts out at 2, min gets reset to 2, and we try to find a smaller value. I say, oh, look, I've got a smaller one at index 3. Oh, I've got an even smaller one at index 4. That's the inner loop. We get to the swap statement. Let's swap the 3 with the 5. We've finished pass 3. We now know after pass 3 there are 3 values sorted. I gets incremented to 3, min gets set to 3, and then we check for a smaller value. Is 5 smaller? No. So we haven't found a smaller value. We get to the swap statement. We swap 4 swaps with itself. Now we've got 4 values have been selected and put in the correct place. We're done. We don't need to make any more passes because 5, the only place it could be, is there. So yeah, it is intro sort. I wanted to finish the example. So the STL can use intro sort. It turns out Visual Studio and G++ use intro sort. We're going to talk about how intro sort works at the end of the quicksort lecture, and we'll also talk about what the Clang compiler uses. It does not use intro sort, at least not the last time I checked. So we'll talk about those, what the STL uses later on. Next lecture, I think. Okay, so there's our example of running through selection sort. Let's look at our analysis. So our analysis says it's n squared over 2 comparisons. Well, it's really n times n minus 1 over 2. So it does that number of comparisons every time. It does n minus 1 swaps in the best, the average, and the worst cases. It does not matter. Selection sort, as written, is completely insensitive to input. It always does exactly the same amount of work. So this is not adaptive. It doesn't change with the input. We cannot, in selection sort, we cannot reduce the number of comparisons. Because to find the smallest value takes n minus 1. To find the next smallest value takes n minus 2. To find the next smallest one takes n minus 3. We cannot change the number of comparisons. This is fixed. But the number of swaps, we could reduce the number of swaps. So let's look at how we could make this a little bit adaptive. What I could do is just add an if statement. And like I said before, I don't usually put if statements and the body of the if on the same line, but I needed it here to be able to fit the notes at the bottom in here. So the only thing we changed about selection sort was we added that if. We said if the indices aren't the same, go ahead and do the swap. So this is the thing that changed, is don't do the swap if the item's already in the correct position. So now our number of swaps can go down. So we have made this adaptive. Let's say slightly adaptive. Because we did increase the number of comparisons. Now this, the n squared minus n over 2, this is the same as n times n minus 1 over 2. I just wrote it differently. This is something we haven't counted until now. This is the number of comparisons of data. And up until now, comparisons of data is all we've been counting. We haven't actually been counting the comparisons on indices. We haven't counted comparisons on indices until now. We've left them out. This one I added in. This is the extra if I is not equal to min. This is the extra comparisons that were added in to save us swaps. So like I said, normally we don't count comparisons on indices. Here I added them in because we specifically added these extra comparisons of indices in to reduce the number of swaps. So it is slightly adaptive now. It tends to be not that big a deal because our number of swaps is already small. It's already linear, where we've got n-squared comparisons. Generally, I wouldn't tend to use the adaptive version of selection sort. If I know it's that close to sorted, I'm probably not going to be using selection sort anyway. So it does make a slight difference in the adaptive version here, but it's not as big a deal as it was with bubble sort, where we went from n-squared to n. Here we're still n-squared comparisons. So what's the nice thing about selection sort? Minimum copying of those items. If objects are really large and that copying is expensive, it's hard to beat selection sort because it never does any more than n swaps of data. And so it does really well when swapping is expensive. It does a decent job for small n. We're going to see a better algorithm coming up when n is small. Now, what's the disadvantage of selection sort? Well, it is n-squared time. It's big theta of n-squared time. It's always n-squared comparisons, no matter what the initial ordering of the data is. All those comparisons have to happen. And the runtime only slightly depends upon the pre-ordering. The adaptive version only makes a small change in the overall time. So up until now, the elementary sorts, bubble sort and selection sort, sorting does this specific task of putting them in order. We want to do it quickly. So far, our two sorts, bubble sort and selection sort, have been O of n squared, but we haven't had a lot of opportunity to improve the complexity. We've just been able to make the best case a little bit better, but there's only been really one change we made. We've cut down the comparisons or we cut down the swaps, one or the other. There was only one improvement to be made in each of them. Insertion sort is still going to be O of n squared, but we're going to have a lot of more opportunities to improve it. Now, when we look at these elementary sorts, bubble, selection, insertion, tend to be based on comparisons and swaps. Now, the better method of getting a really better efficiency is to pick a more complex algorithm like heap sort. But if we're talking, hey, let's do an elementary sort, let's do that 2 loops, nested loops. What we want to do is we want to make that inner loop faster. We can't get rid of the nested loop structure easily, but we can make that inner loop much more efficient. And that's what we're going to do with insertion sorts. We're going to improve that inner loop a lot. So here's the basic code for insertion sort. It's going to compare elements one at a time. It looks on the surface, this right here looks a lot like bubble sort. I'm comparing adjacent elements and swapping them, but the process is slightly different. What insertion sort does is it assumes at each step that because we have a sorted region, we've got a sorted region and we've got to get a new element into its correct place within that sorted region. So let's look at an example of how this works, and then we're going to talk about the code a bit. So right now at the beginning, it's assuming that I have a sorted region of size 1. Because one element is an array of size 1 is sorted. There's no elements out of place in there. So I've got a sorted region of size 1. That's what I equals left plus 1 is doing. Is it's saying, hey, I've got to start out at index I here. That one might be out of order. It has to be put in its correct place relative to the sorted region of size 1. So then we've got an inner loop that's going to move left, and it's going to compare things into the sorted region. So we're going to say, hey, let's compare 2 and 4. 2 is out of order with respect to that sorted region. Let's swap 2 and 4. And now I know I have a sorted region of size 2. 5 has to be put in its proper place with respect to this sorted region. So now we say j starts out equal to I. So I now is 2. So I now is referring to that element. And we start j out equal to I. And we say, hey, I've got to go left. If anything adjacent is out of place, let's swap it. So we compare 5 to 4. It doesn't have to swap. But because j starts out at 2, j goes to 1, because j is still greater than left, we compare 4 to 2. And we don't swap those. After that loop, we know we've got a region of size 3. We've got to put 1 into that region of size 3. So we look at 1 and 5, we swap 1 and 5. We look at 1 and 4, we swap the 1 and the 4. Swap at 1 and 2. And that's our order after 3 passes. We know we now have a sorted region of size 4. Element 3 has to be put in its correct place relative to this sorted region of size 4. So we start going left. We compare 3 and 5. We swap 3 and 5. Compare 3 and 4 and swap them. And if you look at the code, it keeps going. It looks at 3 and 2. It doesn't do a swap. Then it looks at 3 and 2 and 1 and doesn't do a swap. So we could do better. We could stop as soon as we don't make a swap, we know we've got a sorted region. We don't have to go all the way to the left end of the array. Once we find 3 and 2 are good, we really shouldn't compare 2 and 1 anymore. So we've got to make some improvements to this code. So let's look at the complexity before we start improving it. So we've got n squared over 2 comparisons in the worst case. This is our n times n minus 1 over 2. Oh, wait a minute. Let's erase that. That may not be right, because we do compare things that have already been compared. It's still n squared. It might not be that number. So it's about n squared over 2 comparisons in the worst case, and that same number of swaps in the worst case. However, the number of swaps in the average case gets a little bit better. When we go from worst to average, we'll find that, hey, we keep looking left in that array, but we don't actually have to make a swap every time, because that sorted region grows sometimes, and when that sorted region grows, we don't have to do the swaps anymore. So from worst to average, we'll get a little bit better number of swaps, but our comparisons will stay the same. So it is a little bit of this. When we say non-adaptive, this is really, we should say, original version here. The original version is a little bit adaptive on the number of swaps, but not on the number of comparisons. So we'd like to make some improvements. Okay, first thing we're going to do here is we're going to stop using swap. And what we're going to do is we're going to copy items. Now let me do a little example of why this is a good idea. So when I had the point where I was at like let's say I had 1, 3, 4, 5, 2, and I know this region is sorted. I don't actually have to make swaps along the way. I know 2 is the one that's out of place with respect to the sorted region. So what I'm going to do is I'm going to make a copy of the 2, then I'm going to copy 5 over the top of 2. I'm looking for the right place to put the 2. I find that it could move to where the 5 is, but wait, it could move to the 4 is. For it to move to where the 4 is, 4 would have to go here. I don't swap 5 and 4, I just overwrite the extra copy of 5 with the 4. Then I find 2 could go where the 3 is, so 3 overwrites this one. Then I look at 1 and I say, oh, I can't go any further left. 2 doesn't go where 1 does. I'm done with the loop. Now let's copy the 2 here. So I've done less writing to memory. Instead of doing a swap every time, which remember, a swap involves 3 writes to memory, or 3 assignments. Every swap involves 3 assignments. My copy here, every time I copy, my copy does 1 assignment. So have I changed the complexity class? No, but I've changed the constant for the better. So where I used to do like 3 pieces of work, 3n squared swaps, now I'm doing where I did 3n squared amount of work to do the swapping, now I'm going to do 1n squared amount of work to do the copying. So I've improved my constant factor by a large amount. So that's a big improvement, is I'm going to make a copy of this item V, and then I had to move my loop variable j, I had to move it out of the for loop because I'm going to have to remember that value, because after the loop is over I need to know j. I need to know where I left off. So then I've got my for loop doesn't have the initialization anymore. It still needs the semicolon though. I have empty initialization, semicolon, comparison, semicolon, the update condition. And I got rid of the swap, replaced it with an if. So I do if, not a sub j anymore, v. If the value that I'm trying to put into the sorted region is smaller than the one I'm looking at, then overwrite a value with the one to the left of it. This is what happened when we did the, hey, let's overwrite the 2 with the 5. Let's overwrite the 5 with the 4. That's line 8. Line 8 is doing that. Let's copy that 5 one position to the right. Let's copy the 4 a position to the right. That was line 8. Notice now the else is added. If I find that V cannot move any further left, I break out of the inner loop. When the inner loop stops, I put V where it belongs. Line 12 is what put the 2 in the correct position. So line 12 is what put that V back where it belongs with respect to the sorted region. And also notice now, we got another effect out of this. We no longer look further left. If there had been, like, let's say there had been a 0 over here. If there had been a 0 over there, I would stop when I get to 1 and say, oh, the 2's got to come in the position just after the 1, and I never would have looked at 0. My inner loop stopped. So we've really accomplished 2 things here. I've improved my efficiency on constant factor, is I don't do the swap, I do the copy, and I'm able to stop when I reach the correct position for this one. I don't look left any further. Okay, so here is, this is the same code as the previous slide, except I got rid of the code that we crossed out, and I changed the for loop into a while loop. That allowed me to move the comparisons into one place, got rid of the break statement, shortened the code overall. So this didn't make the code any shorter, or sorry, it didn't make it more efficient. It just made it easier to read. So I got rid of the for loop, changed it to a while loop, got rid of the break statement, and now I've got the conditions are all in the while loop. While loop says, while I'm not off the left-hand end, and I have not found the correct place to put it yet. So while I haven't gone off the left end and I haven't found the correct place to put it, I've moved this if. See, this if right here moved up into the while loop. So while I'm not off the left-hand end and I haven't found the right place to put it, I do the assignment. I move a value one position to the right. I copy a value one position to the right, and then I update j. Because I don't have a for loop anymore, I've got to do the update condition at the bottom of the loop. When the while loop ends, this line remained the same. Put v where it belongs with respect to that sorted region. So this allowed me to have code that's a lot easier to read. However, there's something we can do about this. That j greater than left test, it happens n squared times. But it's very seldom false, because as I put things into the sorted region, I usually don't have to go all the way to the left end of the sorted region. Once the smallest value is at index 0, I will never have to go past index 1 anymore, because no one's ever going to swap with 0 any longer. So that test gets done all the time, but it's very, very rarely false. Especially once the smallest value gets to the beginning of the array, the test will never be false. So what I'd like to do is I'd like to get rid of that j greater than left comparison. And the way I'm going to do it is I'm going to use a sentinel value. A sentinel meaning a value that tells me something special. So we said just a minute ago, hey, if the smallest value was in index 0, I would never have to worry about going off the left-hand end, because I'll never have to move past it. So that's what we're going to do. We're going to find the smallest value in the array, and we're going to put it at index 0. So that's what I did here with this code. So this code is added just to get this minimum item and put it in index a sub left. What does that look like? What does that code there look like? It's got a for loop, it's got an if, it's got a swap. It should remind you of something we did earlier today. So that one's actually very similar to bubble sort. It looks like one pass of bubble sort, because that's what I could fit into 2 or 3 lines of code, was one pass of bubble sort. So not only does it put the smallest value in there, it also leaves some pairs behind it are in the correct order, because anything it didn't swap is already good. Anything it did swap is now better than it used to be. So it's leaving some sorted regions behind it, little pairs next to each other that are sorted. We've got the smallest value at index 0, so now I can get rid of this j greater than left comparison, because this one will stop me. When j becomes 1, a sub 0 will be the smallest value, and v less than that will automatically be false. So I've gotten rid of a comparison doing it n squared times. Have I added code? Yeah. This code does O of n work, but it's gotten rid of a comparison that was going to happen n squared times. So my code is still n squared, but I've improved the constants again. So now let's just rewrite that code with all the crossings out gotten rid of, and a little bit more comments added in to make it a little bit clearer. So we find the minimum item, put it at an a sub left, that's our sentinel. Then we make our passes. We had to make another change here. I glossed over this one. We started out left plus 2 is another change we had to make. Remember, before we started out, it used to be left plus 1. It's not left plus 1 anymore. because we did left plus 1 because we assumed there would be a sorted region of size 1. But after I put the smallest value in here, I now have a sorted region of size 2. J in line 3BI. Oh, wow, you are right. I got it correct on that slide, but not this one. So yeah, those should be i's, because that's our loop variable here. Those should be i's. I corrected it on this slide, but not on that one. Yep, I'll fix that. Okay, so we start out at left plus 2 here because now we have a sorted region of size 2. And now we can make less passes through the data. We can make one less pass because we started with a sorted region of size 2. So we've got a sorted region of size 2. The value 2 has to be put in its correct place, ending up with 1, 2, 4. Now we've got a sorted region of size 3, 5. So what happens now? V gets set equal to 5. The inner loop immediately stops because we can't move 5 any further left, and then A sub j equals V, basically 5 overwrites itself, and now we know we have a sorted region of size 4. Then with the value 3, we say I've got to put the value 3 in the correct place. So V is equal to 3, we overwrite the 3 with 5, we overwrite the 5 with 4, then the loop ends, and we overwrite the 4 with the value 3, and we've got the sorted order. So actually we've tried to simplify the out-of-bounds indexing problem, is that we don't have to compare it anymore. We know we're never going to go off the left-hand edge because we're never going to go past index 0, because we will always stop when we get to index 1. Index 1, when we compare index 1 to index 0, will never be false. We never have to proceed with the while loop. Okay, so what about our adaptive one here? So in our adaptive insertion sort, our final insertion sort here, the number of comparisons in the worst case doesn't change. It's still n squared in the worst case. In the average case, it's n squared over 4, but it's O of n in the best case. When I start with a sorted array, it says, hey, I've got a sorted array like 1, 2, 3, 4, 5. I know I've got a sorted region. Let's put a sentinel in there. I do a sentinel. I do the pass-through bubble sort. I go compare, 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 compare. No swaps happen. Now I have a sorted region of size 2. 3. I put V gets 3. Then I discover I can't go any further left. 3 overwrites itself. Then V becomes 4. I discover I can't go any further left. 4 overwrites itself. V becomes 5. I can discover 5 can't go any further left. 5 overwrites itself. And we've done about n comparisons. N for the passive bubble sort, n for each passive insertion sort only looked at one value. It said, let's look 1 to the left. Oh, can't go any further. Let's look 1 to the left. Can't go any further. So in our best case, we do about n comparisons. Really, it's about closer to 2n, but it's still O of n. Our copying, because we're not swapping anymore, our copying in the worst case. Worst case would be like 5, 4, 3, 2, 1. Everything gets swapped every time. In the average case, we've reduced the number of copies, and in the best case, we've reduced the number of copies. So from worst to best, we've improved both the number of comparisons and the number of copies. And we also made that improvement where we don't swap anymore. We save a big constant factor in copying instead of swapping. And so we've got a nice adaptive algorithm here. So what are the advantages of the adaptive insertion sort? More efficient data manipulation. We are copying instead of swapping, cut constant factor by 2 operations. It does fewer comparisons and copies. Only when the one that's being inserted is smaller than the end of the region where it's being inserted do we do those copies. And that sentinel also saved us a large amount of comparisons. We reduced our constant factor by cutting out one of those things that happened n squared times. There's still other things that might happen n squared times, but we got rid of an operation that didn't need to be there. So what about insertion sort overall? So overall advantage of the insertion sort, not just the adaptive version, but overall insertion sort, so the adaptive version compared to, compared to like sorting in general. The nice thing is that we do have a nice behavior when the order is almost sorted. Insertion sort does well. The algorithm was very tunable. We got to make a lot of improvements to it to make it a better sort overall. And after we made all of those changes, this is now the best sort for small values of n. What is a small value of n? Compiler and the library makers test this, and they found that about in the range of 16 to 32, somewhere in that range, insertion sort beats every other sort. Even though it's n squared in the worst case, even in the worst case, it'll do better for a small n than a more complicated n log n sort. It's just really, really hard to beat the adaptive insertion sort when n is small, about 16-ish. Disadvantages, it still has an upper bound of n squared in the worst case. We didn't get around that, but we've made a lot of improvements to it. Now, when we look at our performance characteristics overall here, our runtime is proportional to the number of comparisons, it's proportional to the number of swaps, and with some algorithms like sorting, we can do both. We can look at both scales and see how it does with both of those counts. And our elementary sorts are all quadratic in the worst case time and the average case time. And what we mean here when we said average case, what we mean is that we've got values that are uniformly distributed over their range. So for instance, if I had an array of size 1,000,000, if I rolled up random numbers in the range of 1 to 1,000,000, and that was the ordering, it was the random numbers in a random order, that would be a fairly average case. It's not quite sorted, it's not reverse sorted. Reverse sorted is always the worst. Already sorted is generally the best, but somewhat random is our average case. If we look at them, uniform distributions, they tend to be data that we get from the wild, where we've read in data from an input, tends to be somewhat like this random distribution. And if we look at also, we can look at averaging it over every possible ordering. So with 1,000,000, we wouldn't want to do that. That would be 1,000,000 factorial. But let's say I just had 10 items. 10 items, there's 3.6 million possible orderings. That's 10 factorial. A few of them are, one of them is absolutely the best, one of them is absolutely the worst. A few of them are close to the best, a few of them are close to the worst, and lots of them are fairly random. So the average case there, if I average it over every possibility, is going to be fairly random. That's another way we could say, what is the average? The average is, I average over all possible orderings, then I've got an average case. Now, one way we can analyze this data coming in is we could count the number of inversions. So what I'm going to do is for every item in the array, I'm going to count how many items to the left of it is greater than, the number of items to the left that are greater than this item. So I'm going to count the number of items to the left of this item that are greater than this item tells me how out of place this one item is. And if I do that for every element in the input, I would know how out of order the entire thing is. Now the problem with this is counting. If I want to count, C-O-U-N-T, if I want to count the number of inversions, it's over n squared. So just counting all the possible inversions is going to take me n squared time. So this is not something we would do just to determine, oh, look, it's already sorted, we should use bubble sort. Or it's almost sorted, we should use insertion sort. Too late, I've already done the n squared work to count the number of inversions. So we would use this to talk about data, but we wouldn't make it part of our sorting process. Because if we make it part of our sorting process, we're already at n squared before we even determine that, hey, it's almost sorted, we could use a sort that's got better than n squared best case. Doesn't help. But it's a way to talk about data, and it's a way to talk about in which case would I use a certain sort. So if I knew that my data, if I just knew my data was going to be a certain way, then I would know which sort to use. So for instance, it says here property. So insertion sort and bubble sort use a linear number of comparisons and swaps for data with a constant upper limit to the number of inversions for each element. Now the explanation is a little bit easier to read than that. So it says, i.e., for example, almost sorted means elements are not very far out of place. So that's what this saying is here is for data with a constant upper limit to the number of inversions for each element. For example, if I had something, and it says interpretation, efficient when each item is close to its final position. For example, something like that. There are lots of things that are not in the right place, but everyone that's not in the right place is within like a region of size 2 or 3 of where they should be. So bubble sort and insertion sort both do really well when things are out of place, but they're close to where they need to end up being. Okay, insertion sort uses a linear number of comparisons and swaps for data with a constant number of elements having more than a constant number of inversions. So what this is saying is it's got a small number of elements very far from where they should be. And in the interpretation here is, for example, if I take a sorted region, if I take a sorted array and I push back. So if I take a sorted array and I push back, if I've got something like 1, 3, 4, 5, 6, 7, 8, and I add a 2 to the end, insertion sort works very well on this. Because it says, hey, I do 1 pass of bubble sort, 1 is in the right place, put 3 in the right place, oh, it already is, 4 goes in the right place, it already is. Very quickly I discover in a constant number of comparisons, I discover those are all in the right place, and then it takes a linear number of comparisons and writes to get copies to get the 2 to where it should be. So you might think, wait, wouldn't bubble sort do really well on this? As we wrote it, bubble sort would do really well on this, but it's possible to write bubble sort different ways. Bubble sort can be written to bubble small values to the beginning, that's what we did, but it can also be written with the inner loop in the opposite direction. Bubble sort can be written to bubble big values to the end. This one would not be good in this case. This one would. So as we wrote it, bubble sort would work well in this situation, But if we wrote the inner loop the opposite way, it wouldn't be efficient. But insertion sort always does the order that we showed. It always does the sorted region grows from the left end. But if we write bubble sort with the correct directionality, it would be efficient in this case also. Okay, selection sort runs in linear time for data with large items and small keys. So when we've got a case where, like we said with selection sort, when the writing to memory is what's expensive, and it's much, much more expensive than doing a comparison, selection sort does really well. So like our example that I used earlier of like, hey, I've got these medical records out on disk and I want to reorder them. I really want to reorder them. I'm not going to do an index sort. I really am going to move them around on disk. I don't want to do n squared reading and writing from the hard drive. I don't want to do the n squared writes especially. So I will use the selection sort because the comparing of the like patient ID numbers or blood glucose levels, comparisons of that one integer within the big data is really fast, but I'll minimize the number of writes to the disk by doing a selection sort. So we've got to have a really expensive write compared to a really cheap comparison to make this the best ever. Now we're going to look at a new sort. So we're done with those sorts. We're going to look at something that does things very differently from those. This one's called counting sort. So counting sort here is only going to work if we have a limited number of different keys. And we'll talk about what limited means later on. For example, here I knew I was sorting letters of the alphabet, capital letters of the alphabet. There never ever could have been more than 26. But even more, I knew that they would be in the range A through G. So I knew there would never be more than 7 of them. So what I'm going to do is I'm going to make a pass through the data where I count the number of items. I'm not going to copy the data. I'm not going to move data around. I'm just going to count. I'm going to count, and I go through and I count the number of, so this is the number of A's, B's, C's, D's, E's, F's, and G's. So I count the number of each of them. Then I do the second pass. What I'm going to do is I'm going to compute where each one would start. So the A's have to start at index 0. So A has to start at index 0. Where will the B's start? Well, the B's will start at the same place the A's started plus the number of A's. Tells me 3. That tells me 1. Then where do the C's start? Well, the C's start where the B's started plus the number of B's tells me where the C's should start. So I compute these cumulative offsets of where they would go in the initial array. And in the third pass, what I'm going to do is I'm just going to copy the records to an output container. From the input, I'm going to copy from the input to an output container, and I'm going to put them grouped together by their keys because I know there's only 7 keys. Now, when can we use this? We can only use this when the number of keys is limited. For example, if I was going to count the number of class standings, I can say, hey, there's 4 class standings. There's first-year students, sophomore, junior, senior. Or maybe 6 if I include like master's students and PhD students. So I might have like 4 to 6 categories of student standing. If I was going to count how many people in EECS 281, I want to sort everybody by birthday. Well, I know there's only 366 possible birthdays if we ignore year. I just want month and day. I just want month and day of your birthday. There's 366 possibilities. That's a limited number. What you can't do, and we added this slide because people tried to pull this out on the exam once. They said, ooh, I'll just make an array of size max int. Well, you can't make an array of size max int. For example, on a 64-bit architecture, a 64-bit integer to make two to the 64th 8-byte integers would require 160 million 10 terabyte hard drives. That doesn't fit in memory. This is when we use counting sort, we want to fit it in memory. We got to fit it in memory. Int max does not fit in memory. And if we go to, it's really not even a constant. Int max changes with our computer architecture. If we go to a 128-bit architecture, then we would need 2 to the 128th elements in our arrays. That would be possibly approaching. So the number of particles in the universe is 10 to the 80th, is 2 to the 128th is actually, yeah, that would be bigger than the number of particles in the universe. So you cannot pull out int max and say, ooh, just create an array of int max. So if there's like 6, 366, what would be another thing I could do here? If I was going to count characters in the alphabet, well, capital letters, there's 26. Upper and lowercase, there's 52. ASCII characters, there's only like 128 visible ASCII characters. Actually, it's slightly less than that. Some of them are unprintable. But like ASCII character values, 128. That's a limited number. That's a fixed number. I could use a counting sort. Okay, so here's some example code. This code actually works. So max here, max is the number of possibilities, such as 6 class standings or 366 month-day birthdays. So I've got this vector of student data, and I'm going to sort them by class standing. So this is specific to class standing, because why? Because it's right in here. So I've got a vector of student objects, the input. I create an output vector that's the same size as the input. I'm going to do this because I've got to copy stuff from the input to the output vector. So I've got my vector of student objects for the output, and I've got a vector of counts. I made it a vector of size t. It could have been like unsigned int, doesn't really matter. And I initialized it with the size. When I do this, they all get initialized to 0, because this is the same as doing declare the vector and do a dot resize. Initializes them to their underlying type, which is size t's underlying type is 0. So we've got a vector of zeros. Every count is 0. I run through the loop for every automatic reference to a student. So I could have said, so for auto here, I could have said student instead of auto, but it was a little bit smaller, it fit in there better. So for every reference to a student, look up their class standing and add them to the count for their class standing. So you see a senior, you count up one more senior, you see a PhD student, add one more to the PhD students. So that's our pass 1. Pass 2 is I'm going to figure out, actually, these are, because I've already got the counts, these are cumulative endpoints exclusive. So it's a little bit odd to do it this way, but it was the shortest way to get this written. So before we said we would have like a cumulative offset from the left end. What we've got instead is actually a cumulative offset from the end of a given region. So like if there were 3 first-year students, they would end at index 3 exclusive. So if my counts, for example, if my counts started out like 2, 0, 1, 3, then I would change that count to be, well, you still end at 2, so you end at index 2, you end at index 2 also because there are no sophomores, you end at index 3, and you end at index 6. Because there were 6 students to begin with, the last group must end at index 6 exclusive. So we figure out the cumulative endpoint for each region. That's pass 2. Now we go back through the input. We go back through the input and we say, hey, move to the, or not really move, copy to the output at counts substudent subclass standing -1. So basically we've got in our output so we know we're going to have 2 first-year students. The first-year student that we encounter goes here. The second first-year student that we encounter goes here. So we put them at their, remember this is an exclusive endpoint. Because it's an exclusive endpoint, we subtract 1 to get a real index. So -1 gives us a real index. We put the student there, and we reduce. We say, okay, that now ends 1 position sooner. We move the endpoint 1 position to the left. Yeah, yes, it disregards all the other possibilities of the students. It ignores everything but their class standing, but it copies the whole student object. So because we're looping over the input, remember we copy from the input to the output. We loop through every student in the input once in step 1. We loop through every student in step 2. We copy them to the output. So then after step 3 is done and we've copied everyone to the output, we say, hey, just do a swap. Swap my input vector with my output vector, and I'm done. Now, what's the complexity of this code? Well, I'll give you an answer to line 13. Line 13 is O of 1 because it just swaps pointers and sizes. Well, what about pass 1? When we make this loop through, we looked through all n students. This is O of n, if n is the number of students. Pass 2 is O of max, but max, remember, is a constant. We knew the constant up front. This loop is really O of 1. So pass 2 is O of 1. Pass 3 goes through the students again. That's O of n. So we've got and oh, up here, line 2 was O of n because we were assuming student objects have constructors. So it's O of n assuming that we have to run constructors. Line 3 is O of 1. We just create a vector of a fixed size. So this loop has O of n followed by O of 1, followed by O of n, followed by O of 1, followed by O of n, followed by O of 1. This is an O of n sort. But it has a restriction. The thing we're sorting on must have a small fixed number of values, and you have to know what the values are up front. When we did the get class standing, or the class standing function, we assumed here, we sort of glossed over this, we assumed the class standing was like 0, 1, 2, 3 because we used it as an index. So we've got to have a way, not only do we have to have a fixed number of possibilities, we have to have, at least so far here, we've got to have a way to change that possible value into an index in the range 0 to max, and that has to be a constant operation. So we've got to be able to turn a class standing into an index basically in O of 1 time. So the number of possibilities has to be enumerable up front. It has to have a fixed number of possible values. And no, I don't think it's stable because we go through from left to right, but we put them in a region from right to left. So as written, it's not stable. We could make it stable if we made the individual regions go left to right. But it has a big restriction on when we can use it, though. So here's almost our last slide. So we've got elementary sorts. The bubble selection insertions tend to be O of n squared. Non-adaptive versus adaptive. If we ask you in the future about them, I would say if we ask about bubble sort or insertion sort, in the future, we definitely mean the adaptive version. The non-adaptive, though, I would say selection, really it's either one. Selection has such a small difference in how adaptive it is, it doesn't make much difference which one you're talking about. Counting sort is O of n time. As we wrote it, it's not even an in-place sort. If you are really careful and you know the number of categories up front, you can do this in place. If you're really, really super careful, you don't need the output. But the code changes basically you'll have to modify the code for the number of possible categories. Some sorts execute more quickly in special cases. There's a link there, you can play with that later. Lets you look at different cases, different orderings, best, worst, average, etc. And you can make them run all at once, see which one ends first. And the STL sort, like we said before, the STL sort expects to be given two iterators, start, end, and a natural sort order, meaning it sorts the data type supports operator less than. There's another one, if you don't have a natural sort order, there's an overloaded version with three parameters, start, end, iterator, and a functor. And the functor, A less than B, produces an increasing ordering. We mentioned that previously. Okay, so that's it for the elementary sorts. Next time we're going to be looking at quicksort and things we can do with quicksort and some of the other more advanced sorts that use it, like intro sort. We'll see you in office hours.